Okay, in this video, we're going to talk about how to graph a function and its transformations. So we can graph a function by plugging things in to find points, right? So just like how we were graphing linear, we found a point on the line and another point on the line, and we just drew a line between it. We're going to do something very similar when we're trying to find the graphs of functions. So we know that points on the line, so let me go ahead and label my axes here. So this is the x-axis, and this is the y-axis. And this y is going to represent our value of f of x. I mentioned it briefly in the video on functions, but y equals f of x. We all know that. And if you don't, well, now you do. So our y, the y coordinate, is going to be the value f of x, the value that we get when we plug in x to f. So, and if you're confused on that, what that means, please consider go to check out my video on functions and what they mean. So let's look at this first function here. So f of x equals x minus 3 squared plus 1. Okay, how are we going to graph this? Well, let's take some x values and see what happens when we plug them in. So maybe I'll take, let's see, maybe I'll take 0, 1, 2, I don't know why things are moving. 0, 1, 2, 3, 4, and maybe we'll do 5 as well. Okay, so now all we're going to do is everywhere we see an x on the right-hand side, we're going to plug in our value that we're trying to find. So f of 0 is going to equal 0 minus 3 squared plus 1. That is 3 squared plus 1, 9 plus 1, 10. So my point x, f of x, remember that this is x, y, because y is f of x. This is going to be 0, 10. Okay? F of 1 is going to be 1 minus 3 squared plus 1. 1 minus 3 is negative 2. So it's going to be negative 2 squared, which is the same as 2 squared. So that's going to be 4 plus 1, which is 5. So this is going to be 1, 5. Okay, going into f of 2 is 2 minus 3 squared plus 1. 2 minus 3 is negative 1, so I have negative 1 squared plus 1. Negative 1 squared is positive 1 plus 1 is 2. So this is 2, 2. F of 3 is 3 minus 3 squared plus 1. That's 0 plus 1, which is going to be 1. So the point 3, 1. F of 4 is going to be 4 minus 3 squared plus 1, which is 1 plus 1. 1 squared plus 1, which is 1 plus 1, which is 2. So I have 4, 2. And then f of 5 is equal to 5 minus 3 squared plus 1. 5 minus 3 is 2, so 2 squared plus 1. 2 squared is 4. 4 plus 1 is 5. So this is 5, 5. We have a list of points here that are on the curve f of x. We say they're on the curve f of x, and we can go ahead and plot these points to get an idea of what f of x looks like on a graph. So we'll say the point 0, 10 is somewhere here. This is our point 0, 10. 1, 5, we'll say is about halfway down, so this will be here. This be 1. 2, 2 will be, let's say, here. 3, 1 will be like here. 4, 2 here. And 5, 5 would be somewhere here. And I can draw a line that smoothly interpolates each of my points. And this will be the graph of f of x. And if you kind of take points in between, so say I was to evaluate, I don't know, f of a half, f of 3 halves, f of 4 halves, f of 5 halves, you would start actually finding more points on the line that interpolates smoothly in between them, right? So if I divide the intervals that I'm taking points over, so f of 1 half would be like here, f of 3 halves would be here, and so on and so forth. And so I just start filling in this curve with points. The more points I evaluate, the more of an idea I get of what f of x actually looks like. but for our purposes, we really only need to take a few and just sketch the curve. So this is the graph of x minus 3 squared plus 1. Okay, that's how we graph a function. And now adding, subtracting, multiplying, and dividing a function by non-zero constants in different places does something to their graphs. And we call that a transformation, and we'll talk a little bit more about that in a second. But to kind of get a head start on our discussion, let's take a look at some common graphs of functions. So we call these parent graphs or parent functions, and these are graphs of functions without transformations or without being added or subtracted anything. So f of x equals x, that's the same as y equals x, because remember y equals f of x. Y equals x is just a line that passes through the origin. Okay, you can for all of these, you can verify by plugging in values that this is really what these graphs look like. X squared, it looks something like this. It's a parabola passing through the origin, and it has points negative 1, 1, and positive 1, 1. These are 2 points, and then 0, 0 is a point. And obviously x squared, so if I plug in 2, 2 squared is 4, so I have 2, 4 on the curve, and so on and so forth. X cubed is going to look like this. Okay, so it has the point negative 1, negative 1, and it has the point 1, 1. Negative 1 cubed is negative 1 times negative 1 times negative 1. That's 1 times negative 1, which is negative 1. So negative 1 cubed is negative 1, which is why we get this arm that stretches down. Okay, and then obviously the point 0, 0, because 0 cubed is 0. Okay, 1 over x, remember that when we have x equals to 0, this is not defined, so we have what's called an asymptote here. And it has the point 1, 1, and negative 1, negative 1, because 1 over 1 is 1. So 1, 1, and it has the point negative 1, negative 1. And it gets closer to 0 as we go out towards infinity, and it goes towards negative infinity as we approach 0 from the left, and it goes up to positive infinity as we approach 0 from the right, and it kind of hugs the line y equals 0 as we go out towards infinity. So it looks kind of like that. And then the square root of x, it starts at 0, 0, and it doesn't take any negative value. So it doesn't exist over here because we don't take the square root of negative numbers and get real numbers. Remember, it's not defined. If you want to talk about domain, it's in my video on functions. But the square root of x will look something like this. It also has the point 1, 1, because the square root of 1 is 1. And then it has the point 4, 2, the square root of 4 is 2, and so on and so forth. Okay, and so let's look at some transformations of these parent graphs here. And like I said, you can plug values in and verify that this is what these graphs actually look like. Or if you want to get on a graphing calculator and see what these graphs look like, you'll see that these pictures are pretty accurate. But let's kind of move on. So if we want to move our graph left or right, we add b inside the parentheses of the function. So what that looks like is, for the example, let's look at this first example, x plus 3 squared. Our parent is x squared, right? Because if I was to ignore what's in here, I have something being squared. So my parent is x squared. And remember, x squared looks like this. Okay? And it's worth saying, if b is positive, then we moved left. If b is negative, we move right. So in this case, b is positive. It's 3. It's positive 3. So we take the graph of x squared and we just shift it 3 units to the left. It's positive, so we move it to the left. So this is the graph of x plus 3 squared. Okay, so if this is negative 3, we move it 3 units to the left. So to negative 3 rather than having it touch the axis at 0. Okay. Let's look at another example. The square root of x minus 2. My parent is going to be the square root of x, which looks like this. And if I have the square root of x minus 2, b is negative, so I move things to the right. In fact, I move things 2 units to the right. So I move them 2 units to the right, so my curve is just the same curve, shifted 2 units to the right. And this is the graph of the square root of x minus 2. Okay? Very simple. If b is positive, we move it to the left. If b is negative, we move it to the right. Okay? So moving a graph up or down, so we have f of x plus c. So whatever f of x was, we just add a constant at the end, and that moves it up or down. So let's look at x squared minus 2. So if we look at this, my parent is going to be x squared, and that looks like this, right? We got a parabola that touches at 0. And then x squared minus 2 is just take x squared. If c is positive, we move up. If c is negative, we move down. So in our case, c is negative, we have minus 2, so we move 2 units down to negative 2. And our graph looks exactly the same. Let me draw this a little bit better. Our graph looks exactly the same, except we move 2 units down. Okay? Now I have x plus 3. So my parent graph is just x, and that is a line that passes through the origin. I can get it. Close enough. X plus 3 is just take that line, and instead of having it touch at the origin, have it touch 3 units up. So we just have that. Okay, it's a line with slope 1 that passes through the line, or passes through the point 0, 3. So this is x plus 3. Okay, so we just shifted it 3 units up. Okay, and you might notice that that plus 3 is the y-intercept, right? So we're just shifting 3 units up, because before our y-intercept here is 0. Appeals to your intuition about lines there. So stretching or compressing a graph, we have a f of x. So that's multiplying the entire function by a number. So if a is positive, then if a is positive and less than 1, we are compressing. If a is positive and greater than 1, we are stretching. Stretching. If I can spell. In the vertical direction. If a is negative and less than 1, we flip and compress. If a is negative and greater than, if a is, I'll write it this way. If a is smaller, or a is between -1 and 0, we'll say that. And if a is smaller than -1, then we flip and stretch vertically. Okay, let's look at 3x squared. My parent is going to be x squared. Again, looks like a parabola that passes through the origin. 3x squared. So negative 3x squared says flip it, right? We flip it because it's negative, and it's greater than less than -1, so we stretch it by a factor of 3. So this parabola has points 1, 1, and -1, 1. So if I flip it, it's going to open downward instead of opening upward, and it's going to be stretched in the vertical by 3 units. So it'll have the point -1, -3, and 1, -3, rather than 1, 1, because I'm stretching 3 in the vertical direction. So you can think of what's happening here. I think I can do this like this. So instead of, so what I'm doing to this curve is I'm flipping it. I flip it, and then I stretch it 3 times, like that. So that's what's happening to this curve. Okay. Let's look at 1/2 the square root of x. So our parent curve is the square root of x, so it looks like that. Passes through point 1, 1. Looks like that. And what I'm doing is I'm positive, so I don't flip, but I do compress because it's less than 1. So I'm compressing by a factor of 2. So I literally just if it'll do it here. So I just compress it by a factor of a half. Anyways. So it's about half as tall. So I'll have the point 1, 1/2. Okay, so I just compress it by a factor of 2. Okay. Now general transformations are combining all of that knowledge. So are moving left, right, moving up, down, and stretching, compressing, flipping. So let's look at some general cases here. So I have -3 times x minus 2 squared plus 1. So my parent curve is going to be x squared. That's a parabola that passes through the origin. So what's happening here? Let's take a look. So this number out front takes care of vertical stretch and flipping. So I flip and stretch by a factor of 3. then this stuff inside the parentheses here tells me move left or right. It's negative, so I move to the right 2 units. And then this one on the outside here tells me move up because it's positive, so I move up 1 unit. So what do? I move up 1 unit. So rather than being at the origin, I'm at positive 1. And then I move to the right 2 units, so I'm over here. And then I flip it and vertically stretch by 3. So I'm looking at something that looks like this. Okay? All right. This is what it will look like here. So this is my graph of x squared, and this is my graph of negative 3x minus 2 squared plus 1. Okay? Next, let's move on. So I have 1 over 2 times x plus 1 minus 1. So I'm going to rewrite this actually to make it a little bit clearer what's going on here, because I can rewrite this as 1/2 times 1 over x plus 1 minus 1. Now I can see that I'm going to be compressing by 1/2, or compressing by a factor of 2. I'm going to be moving to the left 1, because of that positive 1, and I'm going to be moving down 1 for my parent graph. So remember, my parent graph is going to be, in this case, 1 over x. So it looks like this, with an asymptote at x equals 0. Now, what I'm doing is compressing by a factor of 2. I'm moving left 1 and I'm moving down 1. So if this is my origin here, my origin of my graph will move, or my center point, I should say, will move left 1 and down 1. So this will be where the origin kind of goes. My asymptote will still be vertical. And then I compress by a factor of 2. So I'm looking at something that looks like this. So it kind of hugs that line more tightly. Okay. There we go. That's what that function would look like. So this is the graph of 1 over 2 times x plus 1 minus 1. Now, any point on this on these curves will be subject to these rules, right? So they'll move up, down, left, right. They'll be moved up, down, left, right, and compressed and stretched by these kind of addition, subtraction, multiplication, and division going on the f of x. So they'll transform in the same way, point-wise. And that kind of wraps up what I want to say about transformations of functions. If you found this video helpful, please consider liking and subscribing. Thanks.